Okay, today guys, this week we're talking about the fundamental theorem of calculus. It's in like sections, 6.3 and 6.4 of the book. Okay, and this is a pretty, as a math teacher goes, is a pretty exciting stuff. Because what this does is it kind of fuses together the two calculuses that Leibniz and Newton created. All right, and you may or may not remember me talking about Leibniz and Newton, that they created calculus pretty much simultaneously. It wasn't the exact same time. There were some years in between, but because of the review process, neither one knew about the other one's work. And so Newton looked at what the calculus we've done so far, the differential calculus, and Leibniz looked at more of the area or integration calculus and this fundamental theorem of calculus. They both came up with it in different ways, and it linked the two together, and it brought it all together, and it made it really, this one powerful mathematical tool that allowed so much innovation to happen later on. And you might say, oh, how is that possible? Well, you just start to think about all the places that calculus applies, and I don't think it's any, I don't think it's overstating it to say that if you didn't have calculus and all of the, this focus, there we go, and all that it offers, you wouldn't have had the Industrial Revolution. You could not have had the creation of all this technology without calculus, because of all the applications it had towards physics and towards engineering and whatnot. So this is like what really brought it all together, this fundamental theorem of calculus. Okay, so just watch. You don't really have to take notes on this. I just want to show you something, okay? So let's say we have a curve right here for ourselves, right? And let me make sure I have my notes here so I can say everything perfectly well, because it is, it's kind of a complicated topic. So we have this curve right here, and we'll say that this is just f of t, and we're just going to make t the variable, right? And the reason we're going to make f of t, we're going to make t the variable, is just because we're going to use x as the upper bound of what we have right here. So that's why we have to put t right there. Okay. So if we are looking at the area, and let's start at some lower bound, and we'll start right here at a. Okay. So if we're going to calculate, if we're going to say what's the area of this shape right here, well, that we've already talked about. That's the integral from a to x of f of t dt. So this is the height. That's the width. We're going from a to x. That's our area. Okay? Right? That's what we've done so far. Okay? We're instead of having an upper bound of like a number, we're just putting a variable there. Okay? The reason we're having that is because we want this to be able to change, and we want to make it whatever we want. We want to make it universal, so that's why we put that there. Okay? In this case, if we're going to think about the instantaneous rate of change of the area, okay, if we're going to do that, hold on, I'm just going to pause this real quick and close the door. Okay, we're back. Sorry about that. I had to close that door on my wife so that I kept feeling like I heard it. I don't know if you heard it, the background noise, but okay. So the instantaneous rate of change of the area, right? That would be if I'm at x. Okay, that area, well, that would be the next rectangle we'd have, and here would be that right there, and the instantaneous rate of change of the area would be. Okay, hold on. I'm sorry, let me get rid of that real quick. Okay, and the instantaneous rate of the change of the area would be just f of x, right? The height at x, and by whatever the change in x is going to be, right? So we'll put dx right down there for ourselves. Okay. So another way to think of this is that remember, that's the change in the area for ourselves, right? So the d is the, I could put delta there as the change in the area, but I put a little d because it's instantaneously, the instantaneous change, so it's infinitely small. Okay, and so that's how much bigger this would be. And so this rectangle right here is the change in the area. That's what that represents. Okay, how much it's going to change there. Now, if I were to take this and divide both sides by dx, okay, I can see that the change in the area in terms of x is the function itself, okay, for myself. Now, remember that this function right here, remember that the area was this right here, okay? So this, I'm going to highlight it so you can see that this area was given by this equation right here. Okay? So if I were going to rewrite this, I'd have the derivative of this whole thing okay? So the derivative of this is the value of the function. Okay? Now at first you look at that and say, well, that's a giant mess, right? But it's really the important thing here is that we can see that if we take the derivative of this change in the area, it'll bring us back to the function. Okay? So if I have a function and I'm going to find the area and then take the derivative of that, it brings me back to the function. So it's undoing. I'm starting with the f of t right here, and it's ending with f of x, and it's just a different variable there, right, we had for ourselves. But you can see that integration and differentiation are undoing each other, bringing me back to where they are. So this shows that integration and differentiation are inverses. Okay? The significance of that is, so if we want to integrate, if we want the inverse operation of differentiation, we do the opposite of differentiation, or the antiderivative. So this tells us we can use the antiderivative to calculate area. Okay, now maybe that was a big jump for you there, but remember, this calculates area, right? If I calculate the area and then take the derivative, it brings back to a function. In order for it to bring me back to what I started with, then this must be the inverse operation of this right here. So the derivative is the inverse operation of integration, so it's going to be called the antiderivative, or the opposite derivative of it, okay, for ourselves. And that's how we can calculate it. Okay? So what does that mean? That means that if I'm going to calculate the area, and let's just say I'm going to make it general, okay? And I have an equation like, right, x squared dx, and I'm going to find the area under the curve of x squared dx. And I know I didn't give any bounds there, right? But we think about this and say, wait, integration is the opposite derivative, or the antiderivative of differentiation, right? So if I take the function here, well, let's think about the antiderivative. And what I mean by that is, what has the derivative of x squared? Well, what has the derivative of x squared? Well, something to the third power has, right? Because if I took the derivative of it, right, then it must have been a power before, right? Yeah, I'm sorry, this must have been the power before. The derivative of something cubed is squared. Okay, that's what we're asking ourselves. What has the derivative of x squared? Now, I'm also going to divide by 3. Why? Because if I took the derivative of x cubed, I'd have 3 times x to the second. But there's no 3 out in front, so I divide by the 3. Okay? So what we're doing is here, this function has a derivative of x squared. Okay? So another way to think of it is, you're reversing your derivative rules. Okay, to get that. So the derivative rules says when you take the derivative, you subtract 1 from the power. Well, if you're doing the opposite of it, you're going to add 1 to the power. Okay, and so the derivative rules say you're going to multiply, right, for the power rule, you're going to multiply the power. Well, we're doing the opposite, so we divide it by that. There's also for this going to be something, we're just going to put a plus a constant number, and that C stands for any constant. Okay, and the reason we write that is if you took the derivative of this, remember that if you take the derivative of this, it should be x squared. If you have a constant number, take the derivative, it's 0, it goes away. So that's why we're going to have that plus c as a placeholder. So this equation is going to tell us the area under the x squared curve. Okay, if you give me some bounds, you say start at this x value and go to this x value, then we can just use that function to calculate it. Right? For example, okay, let's say we have 1 to 3. I'm sorry that this thing is not focusing very well today. Okay, so if I'm going to do it, the antiderivative is x cubed over 3. We just figured that out. We have a plus c there. Okay? We're going to evaluate it at 3 and 1. Notice the notation I'm using. This is the evaluation tool. Right? It's just a line going up and down, and it says I'm evaluating with an upper bound of 3 and a lower bound of 1. So, okay, there we go. Focus back. Okay? And so I'm going to take this 3 and plug it in. Right? Now, this function, that's the antiderivative, that has a name. That's called the big F of x equation. Okay? So, right, that has the big F, capital F of x. Okay? So what we're going to do here is we're going to do f of 3, and then we're going to subtract the value at 1. Okay? So what this is doing is find the area up to 3. This is going to tell you the area up to 3, and then we're going to take away the area up to 1. Okay? That's our process here. So this right here, f of 3, says what's the area from 0 to 3? All right? And we think about that graph, 0 to 3. All right? So it's going to find this area, but we don't want the area from 0 to 1, so that's what this is going to find, and we're going to subtract that away, so we'll be left with that part that was our actual answer at the end. Okay? So we'll take 3, I'll plug it in. I'll take 1 and plug it in. And then I'll subtract them. So that's 27 thirds minus 1 third, so that's 26 thirds. C minus C, that's 0, those cancel out. So this tells me, hey, there's the area, 26 thirds. So I'm using this fundamental theorem of calculus, right? And when I actually calculate it like this is part 2 of the fundamental theorem of calculus. So I'm using the fundamental theorem of calculus part 2 here to get that actual value. But really it all comes back to the fact that, hey, we found here that integration is the inverse operation of differentiation, so we can use our antiderivative to help us calculate some values for ourselves. Okay? Let's say we had a different equation for ourselves, right? And our equation was something like, right, it was sine of x dx from 0 to pi. Okay? We could have trig here. So we say to ourselves, okay, we're doing the integral, so I have to figure out what the antiderivative is. What has a derivative of sine of x? Okay, so we think back and we say, oh, that's cosine of x. The derivative of cosine of x was sine of x, except the derivative of cosine is negative sine of x. Okay, I'm just going to put a negative out in front there. Okay? So I make it work, right? And I'm just adjusting for that sign that we have there. You remember, when you take the derivative of this, it must be this right here. Okay? We have our bounds from pi to 0. Okay? Now, one of the properties we talked about before, if you have a negative sign out in front, you can get rid of that, but also flip the bounds. So I'm going to do that. So that negative sign went away because the bounds got flipped. Notice that. Okay? You can keep the negative if you want. Personally, I lose track of negative signs. I'm not going to keep it. Okay. So now I'm going to do big F of 0 minus big F of pi. Okay? Cosine of 0, that's 1, minus cosine of pi. Cosine of pi is negative 1. So minus negative. So 1 minus negative 1. Right? That's 2. So the area from 0 to pi is 2. Okay? So that's what we have to do for all these examples. As we do it, we just kind of work on finding the antiderivative there. Right? And I'm going to make another video that can give you a bunch more examples on that. Right? So this is the video that you really have to watch. The next one is going to give you more examples. If you feel like you're good, you want to try the homework, go right ahead and do that. But video number 2 will give you more examples in case you need those.